Okay, so welcome to you all in Aerovision. So, my name Ujjwal Srivastava, and I'm doing my masters in IIT Kanpur. So, as I told you in last introduction lecture, I'll start the space dynamics for Get Aerospace for 2026. So let me start. Hope you are doing good. So let me start. Okay. So along with me, you please make your notes, right? And whatever I'm saying, please write on your notebook because my handwriting is not that much good, but still it is okay. So please cope up me in this and write all those things. Okay. So the first things comes, that is your, let me suppose it is lecture 1. Fine. So today we'll do all the basics for the orbital mechanics. So the space dynamics is also called as the orbital mechanics. Why it is called orbital? Because sometimes, not sometimes, because we mostly deal with the uh, orbit that is circular or elliptical. Right. Yeah, we also use hyperbolic orbit uh, or parabolic orbit. We'll discuss all these things in the courses, but mostly we study the circular and elliptical orbit in depth because majorly we focus on this. Reason is because the earth is rotating, and around the earth the moon is rotating in a you know circular orbit or elliptical orbit. So we'll define all these things. What are the planets are moving around the sun, or the planets which is moving around the earth, in which orbit they are moving. So basically all these things are moving in a circular or elliptic orbit. So we'll see one by one what is circular orbit, what is elliptic orbit by the time of the courses. So first let me define some fundamentals. Okay, so write fundamental of orbital mechanics. Okay, so so right, the basics of orbital mechanics. Is Newton's gravitation universal law. That is, or you can say, which describe the forces between two point masses, or you can say masses, doesn't matter. Yeah, that is capital M and small m. I will tell you what is the capital M and small m. Fine. And it has been separated by a vector r bar. Fine. So let me take on masses. This is your mass m. So capital M is nothing but the heavier masses. You can say the heavier mass, or you can say the huge mass, like our Earth. And the small m is your okay. Let me take a small only. Yeah, a small m is your a small masses, you can say. And the center, see, the mass is having the see. Let's suppose this is your a planet. We assume as of now is a planet. So for every planet or every masses, there is something called a center, right? Center of mass for every masses, or it might be planet or something. So the center of masses between the radial distance between the two center of masses of a two. Okay, let me take the center of the distance between the two. Okay, why it is not going? Okay, yeah. So the radius between the two center of a masses is known as your radial distance. It is denoted by r bar. This is basically the radius vector. We can say this is a radius vector because it is showing the directions, right? Because it is showing the directions where the mass is. So and radius because the um, it is relating the two point masses from their center. So basically what Newton's gravitational laws state, let me write. Okay. So it states that there is a force of attraction between any two masses. Please make your own notes, it will be good. And this force is proportional to the product of masses and inversely, or you can say anti-proportional to the square root of, sorry, it's not a square root, the square of the distance between their masses. So you might have studied in your 11th class in chapter gravitation. So the formula is basically F vector is equal to basically the proportion, 1 by 2 times capital M small m divided by the r square. It is a bar because it is a vector. So as you know, if you remove the proportionality sign, so we'll get some constant, and that constant is called the gravitational constant. That is your g capital M small m divided by the r bar square. You can take mod because r is always positive, so you can take mod, no issue. So that is your g m small m divided by r square. You can say like this also. So this is your equation number 1. So let me define what are the things. See, over here g is gravitational constant. Capital M is a mass of heavy body, or you can huge body. A small m is a mass of small body. A small body means compared to the m, that large body. This r is a radius. Okay, so this value I'll give you when I will give all the values, constant values for mass of the earth or something. So that time I will give you in a chart so that you can remember in easy way. Okay. So now I will tell you something. See, please understand this. This is very interesting. In your 11th standard, you might have studied if you have one mass, right, of m, if it is having some acceleration, right, so what you write basically the equation of motion. Basically what you write, F is equal to ma. Here mass is constant, a is the acceleration, F is the force, right? So here, because in our formula there are two masses, right, m and small m and capital M. So we have to write equations of motion for two masses, right? Okay, so I will not erase this. I will keep it here so that you can understand. So let me take geography. Okay, take one reference line. It will be x, y, and some z, right? This is your origin. Okay, let's suppose this is your small mass. So small mass m, right? Let us suppose this is your capital mass m. So what is position vector? So the from origin to any point, that is called position vector, right? Okay, take me here only. Okay, and like this. Basically it will go to centroid. It will also go to centroid. So let me take, this is your position vector 1 and this is your position vector 2. Right. Let me take, if you take two objects, let's suppose if you have two objects, one bigger object and one smaller object. So can you tell me the center of mass? Of course near to the bigger mass, right? So if the mass is increasing in a one side, the center of mass or center of gravity or center of mass, we can say both all the things are the same different thing, but here I'm talking about the center of mass. It shifts toward the bigger mass, right? So let me take the center of mass for these two masses, small m and capital M, right? So let me take the R of C. Let's suppose the distance between the small m and capital M is R bar, okay, and the center of center of, you can say, mass sum is lying between here, because it is a bigger mass, so center of mass definitely will shift towards the bigger mass. Let me take it R C bar, right? So now write the equation of motion for the two body system can be written as, see, actually what I said, na, see, in our 11th standard or 9th standard we had one mass, right? And that mass was moving with some constant, not constant, it can be variable. So with moving with some acceleration, so the force was the F equal to ma. So it was for one body, for one body. But in our case there are two bodies, because see, here also two bodies, because the gravitational field at apply for the two bodies only, because always the masses are attract to each other or repel to each other. So basically it means the two bodies are coming to the picture. So we have to write the equation of motion for two body system. That is why I'm doing all this. So let me drive what is the equation of motion for two body system. So what is the force? See, so the force of M bar will be the capital M into the acceleration of 1. See, so in note, if you have observed anywhere, see, this is your, let's suppose this is your written as R. So this is your position, let's suppose. Okay. If R dot I'm writing, so this is your displacement. And if R double dot comes, and this is your acceleration. See, d dot means what? dr by dt means like with time how the positions are changing. See, this is your position. If with the time the position are changing, that is called displacement. And with the time, if positions are changing twice, like so this is your d square r divided by the dt square. So this is your acceleration. That is why I'm writing m r1 double dot, right? And that is also equal to, you can take minus because it's always attract to each other. So centroidal, it begins from the centroid. That is why I'm taking minus g. You can take also here, I forgot, right? Yeah, from centroid is coming, so you have to write is minus here, minus g capital M small m right? Divided by, I have to write the radius of this 2. So r1 minus r2, you can take the square, right, more of this. Then after I will write for a small mass, it is your small m r2 double dot is equal to minus mg capital M small m divided by the r2 minus r1 power whole square. Now if you add these two, so these are going to be cancelled, right? So if you take, so here you have to take r1, right? So yeah, r1 minus r2, because we have to take the acceleration, right? So we have to subtract this. Then also we have to take r2 minus r1. So if you observe this, these both are opposite to each other. If you take negative from here, so it will be r1 minus r2, right? It is a square, so it doesn't matter. So it will become plus, so it will be 0. So if you add this f of m plus f of small m is equal to m r1 double dot plus small r r2 double dot is equal to 0. Right? This is your question number 2. So basically all these things what I have did here, like you don't need to mug up or remember. Yeah, but you have to go through it so that you can understand how the formulas are coming. The main thing is you have to remember the formulas. You don't need to remember the derivation or whatever I'm writing in between the formula, but you have to go through so that you can understand how the formulas are driving and from where it is coming. So this is called the equation of motion of two body system. Now I'm telling one thing here. See, the force is applied to the capital M. That means what? See, this mass and this mass are attracting to each other or pulling to each other. If it is the same nature, or you can say, see, these are the attracting at this mass is attracting this capital mass, and this capital mass is attracting this small mass. So both are attracting. So on this capital mass here, these are doing some force because it is attracting, right? So this force is due to a small mass, right? At the same time, this capital mass is doing some work to attract this small mass. So they are doing some work. So they are forcing, therefore they are applying the force to attract this small mass. So this force is due to the capital mass, right? And this is your fundamental equation for the equation of motion of two bodies, right? Now let me tell you one thing. Yeah, now let me tell you one thing. Let us, okay, I'm doing the derivations because so that you can understand the things from where it is coming. So now, right, let us not let the position vector to center of mass of M and capital M. Systems are M and capital M system B R C. I've written here. Here the centroid or position vector, you can say, for this system is R C, right? So now this RC will be a small m R2 bar plus capital M R1 bar divided by small m plus capital M. Yeah. So if you observe, this part is from 2 is 0, right? So that means the R of C is equal to 0. That means, what does it mean? This is equation number 3. That means, what does it mean? That is, the center of mass of the two body system is unaccelerated. Okay, because see, if there are two masses, body system masses, so the center of mass is unaccelerated. Reason is because both the mass is having the almost the same, not almost the same forces, but they are attracting, or they are pulling to each other or attracting to each other. So they are applying the forces not equal but different, but the center of mass is not effective, because the both mass is not going to affect any types of uh, affection to each other. That is why the center of mass is unaccelerated. The reason, one example I'm giving you, all the solar system is having them orbit or orbital revolution or something. So they all are doing the revolution around the sun. So these all planets are lying in a same, you can say not plane, for time being you can say the plane, lying in the same plane, and they are riding in the same orbit. If the center of mass is different, or it will be, if it is non-zero, so they all will collide. That is why the center of mass of the two body system, or more than that, is unaccelerated. That is why it is coming 0. Fine. So now from there, I will skip some derivation over here, because it is a little bit tricky, or not tricky, it's long only. So now I'm telling you the story behind this. Let me take, let's suppose this is your capital mass M. Okay, this is your, okay, this is your earth. Let's suppose you can say the capital mass M. Let me take, this is your small mass, this is your moon, this is your small mass. See now, this capital mass is, everyone knows the moon is revolving around the earth, right? So the moon is revolving around the earth because of this capital mass. So the question is, at which acceleration the small mass is moving or revolving around the capital mass, or at which velocity or acceleration this capital mass is rotating the small mass around their center of axis or center of mass, you can say. So I'm going to write the equation for acceleration. So see, the equation for acceleration is g, okay, the capital M plus a small m, okay, divided by r bar divided by r bar cube. That is capital G small m plus capital M divided by r square, you can say, right? So this is acceleration of mass m due to capital M. See, it's getting clear. Let's suppose this is your equation number 4. Okay. See, if there are two masses, okay, so they are applying gravitational force to attract to each other, right? Let me take one bigger mass and one smaller mass. So automatically this bigger mass will try to accelerate this small mass towards their center of mass. And if it is in a orbit, so this small mass uh, start to revolve around this capital mass. Okay, so at what acceleration this small mass is revolving, that is this, right? At the same time, this small mass, it's very good story. See, this is a small mass is having some acceleration, because if it is rotating around any bigger mass, or you can say the earth, if the moon is rotating around the earth, so the moon is a smaller mass, the earth is a bigger mass, so it is having some acceleration. At the same time, it is having some energy, right? So this energy is categorized in two parts, that is your potential energy and one is your kinetic energy, right? It is having some velocity. If it is if it is circular orbit, so it is having some velocity. So all these things will study uh, in a upcoming lecture or videos. So this is your acceleration of a small mass due to the capital mass. So it will revolve around it, right? It will revolve around this. So this is your equation number 4. Now, okay, 34 minutes, fine. Now, as I told you, the small mass is having some energy. So write energy. So whatever I'm doing derivations, it is not mandatory, I'm saying again and again, but once you have to go through it, so that you can understand how the formulas are driving and how it is coming. Because I have studied the same thing in my preparation, and I have never mugged up the derivations or something. I have mugged up only formulas and written in the notes. but I have gone through the steps. What are the steps to driving the formulas, so that I can have some idea if the questions are coming in between the steps, so you will get some idea from where you can apply the uh, formulas, or which concept you can apply into the question. So only we have to go through the derivations or steps. The last thing is, or the final thing is, we have to remember, or you have to mark up the formulas, and that's it. But one thing is, be clear, how the formulas are coming, you have to keep in your mind how it is coming and what is the physics behind this. So see, so there is something called Lagrange equations, right? So basically, the energy we study in space dynamics, that is your potential and your kinetic energy. So basically, we only deal with the Lagrangian equations. So Lagrangian equations deals with energy, both. I said both kinetic energy and potential energy. So let me take first kinetic energy. So it will be subtopic. So okay, what is the not kinetic? So first let me take the potential energy. So consider the potential energy of a system in below figure. So let me draw one figure. The same figure I will take. Okay. This is your small m, no, capital M, sorry. This is your small m. This is your centroidal distance between R. Okay. As you said, it is having some velocities or acceleration. If it is having acceleration, so definitely it will have some velocity. So what is potential energy? It is a mgh, mass as well as due to gravity, and the height. If you would increase the height, then your potential will be definitely increase. But one thing you have to bear in your mind, if the height is infinity, that means undefined, then the potential energy will be 0. So at the same time, if your radius will be infinity, then the potential energy will be 0. It is obvious, right? Because if your distance between the two masses are infinity, that means if they are not attracting to each other, that means the energies are not generating, right? So it is obvious. So now write, if it is let me take black pen. It is conventional to stabilize the potential energy as 0 at R is equal to infinity. Hence, the potential energy at a distance R is defined. Yeah, of course. If it is infinity, so it will be not defined because infinity is an undefined number. That is why I'm taking the distance r, so that it can be defined as the work done. Of course, because it will done some work in moving. The masses from infinity to, see, now we will bring this mass from infinity to the finite mass, finite radius, so that we can have some potential energy. So moving the masses from infinity to the location r. Okay. Let phi be the potential energy. I'm representing one notation for the potential energy, so don't be confused with the phi or something. Yeah. Okay. Potential energy and dr be the change in distance. Of course, if we bring the masses from infinity to the finite number, so there will be a change in distance, so that is taken as a dr in between capital M and small m. So what is work done? W, that is the work done, is equal to F into dr, that is equal to d phi. Fine. So I have to do the integration again. I'm doing the derivation so that we can reach up to the formulas for the potential energy, and I will tell you the field of this potential energy for this small mass, that is equal to phi 0 to phi d phi, is equal to, I'm bringing infinity to r, right? So a small g m divided by the r square into dr. See how I'm writing? I'm keeping the formula for f, which we have derived here. Here, right? I'm not taking negative sign because work is always positive. So now, if you integrate it, will come. If you run the integration, you will come to know this. The potential energy will be the minus g small m capital M divided by the r. So this is a potential energy of a mass small m. I said you right. If there is a one capital mass or one small mass, so if this is a moving with some acceleration, so it is having some energy, right? It is having some energy. So in that energy, one form is potential energy, one form is a kinetic energy. So this potential energy which I have derived here. So this is your equation number 5. Now let me take one thing. See, if r is increasing, the potential energy will be decreasing, but it is wrong, right? Because the potential energy is equal to mg h is nothing but your distance or height, you can say, basically r, right? So if it is increasing, so it must be increase, but here it is decreasing. That is why the negative sign has come into the picture. So if you integrate this, you will get negative sign. So then if you increase the, so this is wrong, so if you increase the r, the PV will be also increase. So this is the right equations for the potential area of a small mass m is revolving around the capital mass M, right? Now let me take the, okay, so let me stop now. It's already 45 minutes, so in next class we'll continue from here and we'll do the kinetic energy, right? Then equation of most of linear equations, and then we'll derive one most important equations, that is called the conic equation. That is your, the you can say the trajectory equation, you can also say. So if the rocket is going to the deep space or space, so what are the trajectories they are following? So it might be parabola, hyperbola, elliptics, or circular, whatever they are following the path. So this everything defined by one equation, that is called the conic equation. So tomorrow I'll derive it, and tomorrow I will uh, teach you how to derive this and how to recognize the trajectory path of any of any space shuttles. So thank you so much for being patience, and please revise up to here, and if you have some any doubt, so please feel free to ask in the comment section. And that's all from my side. And as of now I'm doing my masters, so till now also I'm busy because I have to also the um, study for my coursework and just placements or something, because next year placements are coming, so I also prepare for this. So if I upload the videos after 2 or 3 days or 4 days, so please don't panic, please cope up me. But one thing, I make sure that I will not leave you in the middle of the preparation. I'll finish entire syllabus for the GATE 2026 with all the things which I have told you in last class or last introduction lecture. So please bear patience and stay with me. I will make you IITian, right? Because most of the peoples have a dream to be an IITian and study in IIT. So of course it's amazing feeling in being in IIT. It's a fest, or everything is going nice over here, everything is. So I also upload the videos of the fest or whatever entertaining parts in happening in IIT's Kanpur. So I'll upload also the things, so that you can get some motivations and you'll study basically. So okay, then thank you so much for okay, then thank you so much, and please write your own notes, and make sure you, if you don't understand, read the things again and again, you will understand, and think a little bit, because it's little bit tricky. And if you visualize the things, so the things becomes very easy, and it will be easy only because the derivation parts is almost over, not over, like no, because like we have built our basics, so it will be easy. And just I have told you the things, like what are the accelerations and how the accelerations are going on, and the energy something. So this story is only this because this small mass which is moving with some velocity, some acceleration, some energy, and what velocities are there. So all will find in the upcoming lectures. So thank you so much for supporting me, and please like this video, subscribe my channel, and feel free to ask whatever you want to ask me. And I will be happy to answer your queries, and please ask in the comment box. Thank you so much.